Good evening, and welcome to the Nocturnal Astronomer. I'm your host, Atlas Reed, and tonight we're embarking on a gentle journey to one of the solar system's most captivating worlds. Saturn, the ring jewel of our cosmic neighborhood, awaits us with mysteries that have fascinated humanity for centuries. We'll drift through its atmosphere of swirling storms, glide along its magnificent ring system, and visit the diverse collection of moons that orbit this gas giant. We'll explore how Saturn formed in the early solar system, how it creates its own heat, and why its rings shine so brilliantly in the darkness of space. If you enjoy these types of videos, I'd love it if you could give this one a thumbs up and subscribe to the channel. It really helps me continue creating these peaceful astronomical explorations. And I'm curious, where are you watching from tonight, and what time is it where you are? Drop a comment and let me know. Let's dive in. Saturn has been known to humanity since before recorded history began. Ancient civilizations noticed this bright point of light moving slowly against the backdrop of fixed stars, taking nearly 30 years to complete one orbit around the sun. The Babylonians associated it with their god of justice and fairness, while the Romans named it after their god of agriculture and time. When Galileo Galilei first turned his telescope toward Saturn in 1610, he saw something peculiar. The resolution of his instrument wasn't quite good enough to reveal the true nature of the rings, so he described Saturn as having ears or appearing triple-bodied. It wasn't until 1655 that Christiaan Huygens, using a more powerful telescope, correctly identified these features as a disk or ring surrounding the planet. Saturn resides approximately 1.4 billion kilometers from the Sun, which is about 9.5 times the distance between Earth and the Sun. At this remote location, sunlight takes around 80 minutes to reach Saturn's clouds, compared to just 8 minutes for Earth. This great distance means Saturn receives only about 1% of the sunlight that bathes our home planet. Despite this faint illumination, Saturn shines brightly in our night sky, typically appearing as a steady, yellowish point among the stars. The planet itself is enormous. Its equatorial diameter measures roughly 120,000 kilometers, making it about 9.5 times wider than Earth. If Earth were the size of a marble, Saturn would be comparable to a basketball. Yet despite its tremendous size, Saturn has a remarkably low density. The planet's average density is only about 0.69 grams per cubic centimeter, which is less dense than water. If you could find an ocean large enough, Saturn would actually float. This low density tells us something fundamental about Saturn's composition. The planet is made primarily of hydrogen and helium, the two lightest and most abundant elements in the universe. Saturn completes one rotation on its axis in just 10 hours and 33 minutes, making its day less than half the length of an Earth day. This rapid rotation causes the planet to bulge noticeably at its equator and flatten at its poles. The equatorial diameter is about 10% larger than the polar diameter, giving Saturn a distinctly oblate shape that's visible even in small telescopes. This spinning motion also drives powerful winds in Saturn's atmosphere, creating the bands and zones we observe wrapping around the planet. Saturn belongs to a class of planets called gas giants, though this name is somewhat misleading. While the outer layers are indeed gaseous, the conditions deeper within the planet are far more unusual. Let's take an imaginary descent through Saturn's structure, moving from the cloud tops down toward the mysterious core. The visible surface of Saturn, the layer we see in photographs, isn't a solid surface at all. It's the top of a thick atmosphere composed of approximately 96% hydrogen and 3% helium, with traces of methane, ammonia, water vapor, and other compounds. The temperature at this level, where atmospheric pressure equals Earth's sea level pressure, hovers around -139 degrees Celsius. The pale yellow and gold colors we observe come from ammonia crystals and other compounds in the upper atmosphere. These clouds organize themselves into bands that circle the planet, driven by Saturn's rapid rotation and internal heat. As we descend deeper into Saturn, the pressure and temperature steadily increase. The atmosphere grows denser, gradually transitioning from gas to liquid without any clear boundary. Around 1,000 kilometers below the cloud tops, the pressure becomes so intense that hydrogen begins to behave in unusual ways. By the time we reach depths of about 10,000 kilometers, where pressures exceed 1 million times Earth's surface pressure and temperatures climb to several thousand degrees, hydrogen transforms into a metallic state. This isn't metal in the everyday sense of the word. Instead, the hydrogen atoms are squeezed so tightly together that their electrons break free and move about independently, allowing the substance to conduct electricity like a metal does. This layer of metallic hydrogen makes up the bulk of Saturn's interior and extends perhaps halfway to the center of the planet. The presence of this electrically conductive layer is crucial because it generates Saturn's magnetic field. As the planet rotates, electric currents flow through this metallic hydrogen, creating a magnetic field that extends far out into space, though it's notably weaker than Jupiter's field. At the very center of Saturn, under pressures millions of times greater than Earth's atmosphere and at temperatures approaching 12,000 degrees Celsius, lies what scientists believe to be a core of rock, metal, and ice. This core probably has a mass between 15 and 20 times that of Earth. The term ice here doesn't mean frozen water as we know it. Under such extreme conditions, materials like water, methane, and ammonia exist in hot, dense forms that bear little resemblance to the ice in your freezer. One of Saturn's most intriguing characteristics is that it radiates about 2.5 times more energy into space than it receives from the Sun. This extra energy comes from the planet's interior. Saturn is still slowly contracting from its formation 4.5 billion years ago, and this gradual compression converts gravitational potential energy into heat. Think of it like a giant, slow-motion version of pumping up a bicycle tire, where compressing the gas makes it warmer. This internal heat source drives much of the weather and atmospheric dynamics we observe on Saturn. Saturn's atmosphere is a dynamic realm of winds, storms, and subtle color variations. The banded appearance of the planet results from different atmospheric zones moving at different speeds. The bright zones are regions of rising gas, where ammonia ice crystals form at high altitudes, creating pale clouds. The darker belts are areas where gas descends, clearing away the high-altitude clouds and revealing the deeper, darker layers beneath. The winds on Saturn are among the fastest in the solar system. Near the equator, winds can reach speeds of about 1,800 kilometers per hour, which is roughly 5 times faster than the strongest hurricanes on Earth. These powerful jet streams circle the planet in alternating eastward and westward directions, with each band maintaining its own speed and direction for decades or longer. The energy driving these winds comes from both the Sun's heating and Saturn's internal heat source. Saturn occasionally produces massive storms that erupt in its upper atmosphere. The most famous of these are the Great White Spots, enormous storms that appear roughly once every Saturnian year, or about every 30 Earth years. These storms develop in Saturn's northern hemisphere during its summer season and can grow to encircle the entire planet. The storm of 2010 and 2011 was particularly spectacular, eventually stretching more than 300,000 kilometers around the planet's circumference. These tempests are thought to be convective events, where warm gas from deep in the atmosphere rises explosively through cooler layers above, creating towering thunderstorms and turbulent winds. At Saturn's North Pole sits one of the solar system's most geometrically peculiar features, a massive hexagonal jet stream. Each side of this hexagon spans about 13,800 kilometers, wider than Earth's diameter. The hexagon rotates with a period of 10 hours and 39 minutes, slightly slower than the planet's interior rotation. Scientists have studied this feature extensively since its discovery by the Voyager spacecraft in the early 1980s, and it has remained remarkably stable for decades. The hexagon is essentially a standing wave pattern in the jet stream, a phenomenon that can be reproduced in laboratory experiments with rotating fluids. Inside this hexagonal structure lies a swirling vortex, a hurricane-like storm anchored at the pole itself. The South Pole hosts a more conventional but equally impressive feature, a hurricane-like vortex with a well-defined eye measuring about 8,000 kilometers across. Unlike hurricanes on Earth, which derive their energy from warm ocean water, this polar vortex is powered by Saturn's internal heat and the dynamics of the atmosphere itself. Saturn's atmosphere also produces lightning, though it's quite different from terrestrial lightning. The lightning on Saturn occurs deep within the clouds, producing radio bursts that spacecraft can detect. Individual storms can produce lightning bolts thousands of times more powerful than those on Earth, with some storms generating continuous electrical activity for months. These electrical discharges are associated with the convective storms that occasionally erupt in Saturn's atmosphere, where rapid updrafts and downdrafts cause ice particles to collide and build up electrical charges. Saturn's rings are perhaps the most recognizable feature in the entire solar system. Extending outward from the planet for hundreds of thousands of kilometers, yet often measuring only 10 to 30 meters thick in most places, the rings create a stunning disk that appears almost impossibly thin when viewed edge-on. These rings aren't solid structures, but rather countless individual particles, ranging in size from tiny grains smaller than sand to chunks larger than houses, all orbiting Saturn independently. The main ring system consists of several distinct regions, designated by letters in the order they were discovered rather than their position. Starting from the planet and moving outward, the main rings are Ring D, Ring C, Ring B, Ring A, Ring F, Ring G, and Ring E. Ring C appears somewhat transparent and ghostly, earning it the nickname Crepe Ring. Ring B is the brightest and most massive of the rings, containing the majority of the ring system's total mass. A dark gap called the Cassini division, about 4,800 kilometers wide, visually divides Ring B from Ring A. The Cassini division isn't completely empty but contains less material than the brighter regions on either side. The composition of the ring particles is primarily water ice, which explains why the rings are so bright and reflective. The ice is remarkably pure, reflecting between 60 and 90% of the sunlight that strikes it. Mixed with the ice are smaller amounts of rocky material and organic compounds that give some rings a slightly darker or more tan appearance. The particles are distributed in intricate patterns, tight spirals, rippling waves, narrow strands, and knotted clumps that shift and change over time. One of the most fascinating aspects of Saturn's rings is their surprising youth. Several lines of evidence suggest the rings may be only 10 million to 100 million years old, far younger than the solar system itself or even the age of Saturn. The rings are simply too bright and clean to be ancient. Over time, ring particles should become darkened by bombardment from meteoroids and coated with dust from comets, yet Saturn's rings remain brilliantly reflective. This suggests either the rings formed relatively recently, or some process continually cleans and rejuvenates them. How did the rings form? Scientists have several theories. The rings might be the remains of a moon that wandered too close to Saturn and was torn apart by tidal forces. There's a distance from any planet, called the Roche limit, inside which tidal forces become stronger than the gravity holding a moon together. For Saturn, this distance is about 2.4 times the planet's radius, and most of the bright rings lie within this zone. Alternatively, the rings might have formed from debris left over from a collision between two moons, or from a comet that strayed too close and was shredded by Saturn's gravity. The intricate structure of the rings results from gravitational interactions with Saturn's many moons. Some small moons orbit within the rings themselves, called embedded moons, and their gravity creates gaps and waves in the surrounding material. Other moons orbit just beyond the main rings, and their repeated gravitational tugs shepherd ring particles into narrow bands or clear out gaps. Ring F, for example, is confined by two shepherd moons named Prometheus and Pandora, whose gravity keeps the ring particles in a narrow band. The relationship between Saturn's rings and its moons creates some of the most intricate dynamics in the solar system. Dozens of small moons orbit among and near the rings, and their gravitational influence sculpts the ring material into elaborate patterns. Understanding these interactions requires us to think about how gravity works not just as a simple attractive force, but as something that can push, pull, shape, and organize matter across vast distances. Consider the Cassini division, that prominent dark gap in the rings. While it appears empty from a distance, it actually contains some ring material, just much less than the bright regions on either side. The reason for this relative emptiness is a gravitational resonance with Mimas, one of Saturn's inner moons. Particles orbiting in the Cassini division complete exactly 2 orbits around Saturn for every 1 orbit of Mimas. This 2-to-1 resonance means particles encounter Mimas's gravitational pull at the same point in their orbit repeatedly, and these repeated tugs gradually nudge the particles into different orbits, clearing out the gap over time. It's similar to pushing someone on a swing. If you push at just the right moment with each swing, your repeated small pushes can create a large effect. The moon Prometheus provides another beautiful example of gravitational sculpting. Prometheus orbits just inside ring F, and as it passes ring particles, its gravity pulls some of them inward, creating dark channels in the ring. These channels appear as dark streaks that follow behind the moon, marking its gravitational wake through the ring material. Because Prometheus and the ring particles move at slightly different speeds, these streaks slowly shift and blur over time, creating a pattern that changes from month to month. Some of Saturn's smallest moons actually orbit within the rings themselves. Pan, a small moon just 28 kilometers across, orbits within the Inky Gap, a 325-kilometer wide opening in Ring A. Pan's gravity keeps this gap clear of ring particles, but it does more than that. Ring material near the gap edge gets pulled toward Pan, creating wave patterns that ripple through the rings like wakes behind a boat. These waves can be seen in detailed images as subtle corrugations extending outward from the gap. Another embedded moon, Daphnis, orbits within the Keeler Gap in the outer Ring A. Daphnis is even tinier than Pan, measuring only about 8 kilometers across, yet its gravity is sufficient to create magnificent wave patterns at the edges of its gap. The waves reach heights of up to 1.5 kilometers above the ring plane, creating scalloped patterns that look almost like a decorative edging. The outermost regions of Saturn's ring system are even more diffuse and extended. Ring E, for instance, stretches from about 180,000 to 480,000 kilometers from Saturn's center, making it by far the largest ring. Unlike the main rings, which are confined to a thin plane, Ring E has significant vertical thickness, perhaps exceeding 2,000 kilometers in height. This ring is continuously supplied with material from the moon Enceladus, which orbits within it. Enceladus spews water vapor and ice particles into space through geysers at its south pole, and this material spreads out to form Ring E. Ring F deserves special mention for its bizarre and ever-changing appearance. This narrow ring, located just beyond the outer edge of Ring A, displays braids, kinks, and clumps that shift dramatically over short timescales. Ring F seems to be in a constant state of disruption and reorganization. Small moonlets embedded within the ring, perhaps 10 to 100 meters across, collide with ring particles, creating temporary clumps and streamers. The two shepherd moons, Prometheus and Pandora, continually perturb the ring from inside and outside, adding to the chaos. Recent observations suggest that Ring F might be fed by material pulled off the surfaces of these small moonlets when they collide with other ring particles. Saturn's family of moons is one of the most diverse and fascinating in the solar system, with 146 confirmed moons as of current counts, ranging from tiny, irregular chunks of rock and ice just a few kilometers across to the giant moon Titan, which is larger than the planet Mercury. These moons formed from the same disk of material that created Saturn itself, though some of the smaller, more distant moons may be captured asteroids or comets. Titan stands apart as the second largest moon in the solar system and the only moon with a thick atmosphere. With a diameter of 5,150 kilometers, Titan is about 1.5 times larger than Earth's moon. What makes Titan truly exceptional is its dense nitrogen atmosphere, which is actually thicker than Earth's atmosphere at the surface. The atmospheric pressure at Titan's surface is about 1.5 times Earth's sea level pressure. This thick atmosphere creates a haze of organic molecules that completely obscures the surface in visible light, giving Titan a featureless, orange appearance through conventional telescopes. The temperature on Titan's surface hovers around -179 degrees Celsius, cold enough that water ice is as hard as rock. At these frigid temperatures, methane and ethane can exist as liquids, and Titan has weather systems and a hydrological cycle based on these hydrocarbons rather than water. Radar observations from the Cassini spacecraft revealed lakes and seas of liquid methane and ethane near Titan's poles, some of them hundreds of kilometers across. Titan has rain, rivers, and coastlines, all shaped by flowing liquid hydrocarbons. The Huygens probe, which landed on Titan in 2005, revealed a surface of rounded pebbles made of water ice, shaped by flowing liquid methane. Titan's thick atmosphere and surface conditions make it one of the most Earth-like worlds in the solar system, despite the extremely cold temperatures and exotic chemistry. The moon has seasons, clouds, and even dust storms. Organic chemistry proceeds vigorously in Titan's atmosphere, creating molecules that rain down onto the surface and may accumulate in lakes and seas. Some scientists speculate that Titan could harbor unusual forms of life based on liquid methane rather than water, though this remains purely theoretical. Moving inward from Titan, we encounter Enceladus, a small moon only about 500 kilometers in diameter, but arguably even more exciting than Titan for the search for life. In 2005, the Cassini spacecraft made a startling discovery: massive geysers of water vapor and ice particles erupting from cracks near Enceladus's south pole. These geysers shoot material hundreds of kilometers into space at speeds of up to 400 meters per second, with some particles escaping Enceladus entirely to feed Saturn's Ring E. The source of these geysers appears to be a subsurface ocean of liquid water beneath Enceladus's icy crust. Tidal heating from Saturn keeps this ocean liquid despite the moon's small size and frigid location. As Enceladus orbits Saturn, gravitational forces flex and squeeze the moon, generating heat through friction. This is similar to how repeatedly bending a wire back and forth makes it warm up. The geysers erupt from 4 prominent cracks near the South Pole, nicknamed the Tiger Stripes, where the ice is thinner and fractured. What makes Enceladus especially intriguing is that Cassini detected organic molecules, salts, and molecular hydrogen in the geyser plumes. The presence of hydrogen suggests chemical reactions between the ocean water and hot rocks on the seafloor, reactions that could provide energy for microbial life. All the key ingredients for life as we know it appear to be present in Enceladus's ocean: liquid water, organic molecules, and an energy source. Other notable moons include Mimas, famous for its giant impact crater that makes it resemble a certain fictional space station, Iapetus with its mysterious 2-toned coloration, one hemisphere bright and one dark, and Tethys with its enormous canyon system stretching nearly 3/4 of the way around the moon. Each of these moons tells a story about the history of the Saturn system, recording impacts, tidal forces, and geological processes in their scarred and varied surfaces. To understand Saturn and its system of rings and moons, we need to travel back more than 4.5 billion years to the birth of the solar system. Our solar system formed from a vast cloud of gas and dust, perhaps 10,000 times more massive than the Sun is today. Something, perhaps a nearby supernova or the passage of a shock wave through the galaxy, caused this cloud to begin collapsing under its own gravity. As the cloud collapsed, it began to spin faster, much like a figure skater spins faster when pulling in their arms. This rotation caused the cloud to flatten into a rotating disk with a dense, hot center where the Sun would eventually ignite. In the disk surrounding the young Sun, dust grains began sticking together through collisions, gradually building up larger and larger clumps. Close to the Sun, where temperatures were high, only materials with high melting points like rock and metal could remain solid. Further out, beyond what scientists call the frost line, temperatures were low enough for water ice to remain frozen. Saturn formed in this cold, outer region of the disk where ice was abundant. The process likely began with a solid core of rock and ice, perhaps 10 to 20 times Earth's mass, that formed relatively quickly over a few million years. Once this core grew large enough, its gravity became strong enough to capture and hold onto the abundant hydrogen and helium gas in the surrounding disk. Over perhaps another few million years, this core accumulated an enormous envelope of gas, growing into the giant planet we see today. The timing was crucial. Giant planets like Saturn had to form quickly, within about 10 million years, before the gas in the disk was either swept up by the Sun or blown away by solar radiation and stellar winds. Jupiter, being closer to the Sun where the disk was denser, likely formed first and faster. Saturn followed, but by the time it was growing, less gas remained available, which may explain why Saturn is smaller and less massive than Jupiter. Saturn's rings and moons likely formed from the same disk of material that surrounded Saturn during its growth. The moons grew from countless collisions of smaller bodies, gradually sweeping up material in their orbital zones. The rings may be younger, perhaps formed much later from a destroyed moon or a captured comet. The exact sequence of events remains a subject of active research and debate. Over the billions of years since formation, Saturn has slowly evolved. The planet continues to contract very gradually, releasing the internal heat that powers its atmospheric dynamics. The rings have probably changed significantly, perhaps being destroyed and reformed multiple times over Saturn's history. Moons have shifted their orbits through tidal interactions with Saturn and with each other. Some moons may have formed where they are now, while others may have migrated inward or outward over time. Recent research suggests that Saturn's rings may be quite young, perhaps only 100 million years old or less. If true, This means Earth's dinosaurs might have lived under a ringless Saturn, and the magnificent ring system we see today is a relatively recent addition to the solar system. The implications are profound. If rings are temporary features that come and go, then we're fortunate to live in an era when Saturn possesses such a spectacular display. For thousands of years, humans observed Saturn as simply a bright, yellowish point of light moving slowly against the stars. Everything changed when the telescope was invented in the early 17th century. Galileo's first observations in 1610 were puzzling, as his small telescope showed Saturn as having two strange appendages or bulges that he couldn't quite resolve. By 1612, these features had disappeared, which thoroughly confused Galileo. We now know he was seeing the rings at different angles as Saturn moved in its orbit. When the rings were nearly edge onto Earth, they effectively vanished from view in his small telescope. Christian Huygens solved the puzzle in 1655, proposing that Saturn was surrounded by a thin, flat ring. Giovanni Domenico Cassini discovered the gap in the rings that now bears his name, and realized the rings must be composed of countless small particles rather than a solid disk. As telescopes improved through the 18th and 19th centuries, astronomers discovered more moons and detected additional structure in the rings. The space age brought unprecedented views of Saturn. Pioneer 11 flew past Saturn in 1979, providing the first close-up images. Voyager 1 arrived in 1980, followed by Voyager 2 in 1981. These spacecraft revealed Saturn's atmosphere, rings, and moons in stunning detail, discovering new moons, ring features, and atmospheric phenomena. The images transmitted by Voyager remain iconic even today. The Cassini spacecraft, which arrived at Saturn in 2004, represented a quantum leap in our understanding of the Saturn system. For 13 years, Cassini orbited Saturn, observing seasonal changes, discovering new moons, studying Titan in detail, and making the groundbreaking discoveries at Enceladus. The spacecraft completed 294 orbits of Saturn before deliberately diving into the planet's atmosphere in 2017 to avoid any possibility of contaminating Enceladus with microbes from Earth. From Earth, Saturn remains an impressive target for amateur astronomers. Even a small telescope reveals the rings and can show the gap between Ring A and Ring B on nights of steady atmospheric conditions. Larger telescopes reveal cloud bands in the atmosphere and several of Saturn's larger moons. The best time to observe Saturn is when it reaches opposition, the point when Earth passes between Saturn and the Sun, placing Saturn opposite the Sun in our sky and at its closest approach to Earth for that year. The view of Saturn changes dramatically over time due to the tilt of Saturn's rotation axis. Saturn's axis is inclined about 27 degrees from perpendicular to its orbit, similar to Earth's 23.5-degree tilt. This means Saturn experiences seasons, each lasting about 7 Earth years. As Saturn moves around the Sun, we see the rings from different angles. At some points, the rings appear wide open, tilted toward us at their maximum angle. About 15 years later, we see the rings edge on, and they seem to vanish because they're so thin. Then over the next 15 years, the rings gradually open up again, but this time we see them tilted from the opposite side. Future missions to Saturn are in the planning stages. A proposed mission called Dragonfly, currently scheduled for launch in 2028, would send a rotorcraft lander to explore Titan. This flying probe would take advantage of Titan's thick atmosphere and low gravity to fly between multiple landing sites, studying the moon's organic chemistry and searching for signs of prebiotic processes. Another proposed mission would focus on Enceladus, perhaps orbiting the moon to study its geysers in detail or even landing to search for signs of life in the subsurface ocean. Saturn continues to surprise us with each new observation. Recent studies using data from Cassini have revealed that Saturn's rotation period is harder to measure than scientists expected, that the rings may be influencing Saturn's upper atmosphere, and that the planet's magnetic field is remarkably symmetrical. Each answer leads to new questions, ensuring that Saturn will remain a focus of planetary science for generations to come. And on that note, we conclude our peaceful journey through the Saturn system. We've traveled from the ancient observations that first identified Saturn as a wanderer among the stars, down through the layers of its vast atmosphere to the metallic hydrogen ocean within, across the shimmering rings with their intricate structures and embedded moons, and out to the diverse family of satellites that includes the enigmatic Titan and the potentially life-harboring Enceladus. We've explored how this magnificent planet formed in the early solar system, how it continues to evolve today, and how future missions may unlock even more of its secrets. Saturn reminds us that our solar system contains worlds of astonishing beauty and wonder, each with its own story to tell. The rings that grace Saturn are unique in their prominence and accessibility, offering us a window into orbital dynamics and gravitational interactions that play out across the cosmos. The moons surrounding Saturn represent laboratories for understanding ice, organic chemistry, and even the possibility of life in environments radically different from Earth. Thank you for joining me on this exploration. I hope this journey to Saturn has given you a sense of peace and wonder about our place in the universe. Until next time, keep looking up